Okay, our last, kind of the fifth thing that's important for chapter 16 is thinking about reaction mechanisms, rate determining steps, and how catalysis works. So remember, reaction mechanism is a proposed or a hypothetical sequence of single or what we call elementary reaction steps, and we need to validate them. In order for those that proposed sequence of elementary steps to be valid, they must sum to the correct overall equation. They must have reasonable molecularity, which means you don't propose elementary steps that are anything less than unimolecular, which is a decomposition reaction, or bimolecular, two things coming together. And they also must obey the experimentally observed rate law. And this is the key thing, that if your proposed mechanism does not obey the experimentally observed rate law, it's not a valid mechanism. And part of thinking about that mechanism validity is realizing that when you have more than one step to sum up for an overall reaction, one of those reaction steps is going to be what we call rate limiting. So the elementary step that's the slowest. And again, it will have a rate law that must match the observed law. You must obey the experimentally observed rate law. So we're going to walk through a couple of problems here. The first one that we'll do in an in-class problem will be an easy problem when the first step is rate limiting. Then we'll walk through a harder example when the first step is fast. And again, we can think about using these to apply to reaction energy diagrams. So this first sample problem is not really validating a mechanism. We're not talking about slow or fast steps. It's just making sure that we understand the idea of a reaction mechanism. All right, so for this first problem, they provide elementary steps for a proposed reaction mechanism. And so the first thing asked us to do is to write the overall balanced equation. So this is not unlike when we were doing problems with Hess's law, where we'd have to add up individual reactions to sum to the overall reaction. So that's what we're going to do here. So we can see here that anything that appears on the right side and the left side of the reaction is going to cancel out. So this guy is going to cancel out. Anything that appears on the same side of the equation, we can sum together and add a coefficient to indicate that we have more than one of those. So in this case, we're going to have two NO2Cl gases. That takes care of everything that was on the left side as a reactant. Okay. Anything that's on the right side here, again, terms that are similar, we can combine. And we've got Cl2. It doesn't specifically ask us for this problem, but chlorine as an atom is important. So Cl is an intermediate. So we define an intermediate as a species that is generated in one step but consumed in another. Okay, so it's not going to appear in the overall equation. Part B, I'm actually just going to write up here because Part B asks us to determine the molecularity of each step. And when something asks you to determine molecularity, it's very simple. You just need to count the number of molecules that are reacting. So for our first one, it's just the decomposition of NO2Cl. So only one molecule is reacting, and so this is unimolecular. For the second elementary step here, we have two molecules that are interacting, and so that would be bimolecular. So molecularity is really straightforward. Just count the number of reactants you have, prefix unimolecular for 1, prefix bimolecular for 2. Termolecular would be used for 3, but again, that's not going to tend to be a valid part of a mechanism, is to have an elementary step with more than 2 species interacting. Now the last thing here, we have to make sure that we reconcile something that I told you do not do early on. When we are writing rate laws, we talked about the importance of not using coefficients to determine the exponents for your rate laws. Now, if we know that it is an elementary step, then when we're writing rate laws, we know that reaction coefficients become the exponents for order. The only time you can do that is if we know it's an elementary step. Okay, so for reaction 1, we still write rate laws as rate equals rate constant times the concentration of any reactant raised to the power, now that is a coefficient, and we can do that. It's really important that you realize this if we know or are proposing that it's an elementary step. Only one reactant, no coefficients for this first problem, so here's the rate law for that first elementary reaction. For the second elementary reaction, again, rate equals rate constant times the concentration of species raised to the power that are coefficients. Again, we can do that if that's an elementary step. There's no coefficients with either of these, but that's what we have as the rate law for each of these. Now, as we're going to get to in our next two in-class problems that I'll work through in videos here, we can propose whether one of these steps is going to be slow or not. If we propose that the first step is slow, okay, that's going to be fairly easy to think about because the observed rate law should match this rate law. If the second step is the slow step, that gets complicated. So to think about how to validate a mechanism when you're given information as to which step is rate determining, make sure to look at the next two videos which deal with a slow initial step and a fast initial step.